So far we've been looking at independent trials, and in terms of sampling, that's been drawing with replacement. But when you're sampling from a group of people, it's rather unnatural to sample with replacement. You don't want to throw the person back in the pile once you've picked them. You want to pick a different person the second time around. So we're now going to look at sampling without replacement. And random draws without replacement are called simple random samples. So let's take a population that has 4 women and 6 men. Yes, it's a tiny population, but we'll start small. And suppose we're drawing a simple random sample of size 5. What does that mean? That means we are drawing 5 times at random without replacement from these 10 people. And the question I'm asking is, what is the chance of getting 3 women and 2 men in the sample? Is that possible? Sure, it's possible. 3 women plus 2 men equals the 5 people, so this adds up correctly. And you can certainly get 3 out of 4 women and 2 out of 6 men. So let's see what the chances are. The way we're going to do this is just by counting. Let's forget the detail here of how many women and how many men we want. Let's just see how many samples we can get. We have 10 people and we're choosing 5. How many different sets of 5 can we choose from 10 people? How many different ways are there to choose 5 people out of 10? Well, that's exactly what 10 choose 5 does. The total number of different samples that you can get is 10 choose 5. And just to recall the calculation, that's 10 factorial divided by 5 factorial times 10 minus 5 factorial. So that's 10 factorial divided by 5 factorial times 5 factorial. And if you do all the cancellation, you will get 252. And that's how many different sets of 5 people you can choose from your population of 10. Now, all of those choices are equally likely. There's no group of 5 that is more likely to appear than any other, and that can be proved, but I think it's intuitively clear. So if we want to find the chance of getting 3 women and 2 men, what we need to do is to count how many samples give you that feature, and then divide by 252, and you're done. So we need to count the number of samples that have 3 women and 2 men. Let's simplify that problem. How many ways can we pick 3 women? Well, we've got 4. We've got to choose 3, and that's exactly what 4 choose 3 does. The number of different triples of women is 4 choose 3, and that's an easy calculation. That is 4. Similarly, the number of pairs of men is 2 men out of 6 men. 6 choose 2, and that's 15. So what I want is a set of 5 people, 3 of which are women and 2 are men. So what do? Well, I pretend I've chosen the triple of women, right? So I've got 3 women that are just sitting there. And now I want to choose a pair of men. How many ways can I do that? I've got 15 different pairs that I can choose for that single trio of women that's sitting down. So that's 15 distinct samples right there. And how many different trios could I have chosen? 4. So for each of those 4, I have 15 different pairs of men that I can choose. And so in all, I have 4 times 15 possible samples that contain 3 women and 2 men. The number of triples of women, and for each of them you have these many pairs of men. That's counting by products. It's called the product rule of counting. And that's it, we're done. This is the number of samples of the kind we want. This is the total number of samples, and so the probability of getting 3 women and 2 men is just 1 divided by the other. The number of samples of the kind we want divided by the total number of samples. And that's 60 divided by 252, and that's just under 24%. This is a special case of a calculation that is derived from a formula that has a most impressive name. It is the hypergeometric formula that comes from a certain mathematical series that I won't go into here. And the situation is this. You have a population, and the typical notation is capital N for population size. And then in the population, you have some good elements and bad elements. These were what we were calling successes and failures in the last segment. And the notation for the number of good elements is capital G. So just to be clear, the number of bad elements then is everything else. It's capital N minus capital G. From this population, you are going to select a simple random sample of size little n. That means you are going to make little n draws at random without replacement from this population. And the question that you're going to answer is, how many good elements can I get in the sample? And what's the chance of getting a certain number of good elements? And that chance is going to be given by the hypergeometric formula, which is exactly the thing that we derived in a special case just a little while ago. If you choose a simple random sample of size little n out of a population of size capital N, the total number of possible samples is capital N, choose little n, population size, choose sample size. And they're all equally likely. If you want little g good elements, then the number of distinct samples which have little g good elements and the rest from the other group is number good in the population, choose number good that you want in the sample. Number not good in the population, choose number not good that you want in the sample, multiplied together, because for each choice of the g good elements you have these many choices of the non-good elements. So how is this connected to anything that we've been doing? Well, it's connected in the sense that for the last segment or so we were talking about successes and failures. Success-failure trials, yes-no answers to questions. And here is the same situation, it's just the conventional terminology is a little different. It's good and bad, but that's the same as successes and failures, or yeses and nos, or ones and zeros. And so this formula is analogous to the binomial. It gives you probabilities for the number of successes in success-failure trials. But it's different from the binomial because in the binomial setup, the trials were independent. Coins, dice, draws with replacement, and now the trials are draws without replacement. So you've lost the independence. But you are still counting how many successes you have in a sequence of trials. A couple of examples now to make sure we can use this thing. So I'll start with a deck of cards. I've got a standard deck which has 52 cards, I remind you, and I'm going to deal a bridge hand. In the game of bridge, a hand has 13 cards. And I want the chance that my hand contains 2 aces. I'll remind you also that the deck of 52 cards contains 4 aces total. So what am I doing here? I am dealing 13 cards out of 52. That is a simple random sample of 13 out of 52 cards, because cards are dealt without replacement. So my population size is 52. That's my whole deck. My simple random sample size is 13. That's the size of my hand. And now I need to define what is a good element. Well, what am I counting? I'm counting aces. Those are the good elements. How many are there? Well, in the deck, there are 4. How many do I want? I want 2. So it's a straight hypergeometric setup with a population size, good elements in the population, sample size, good elements in the sample that we have identified. So all we need to do now is plug in to the formula that we developed. The total number of possible hands is 52, choose 13. The number of hands with 2 aces is number of aces, choose 2. Number of aces, choose the rest of the cards. And you'll have noticed that good elements plus non-good elements adds up to the total number of elements. Good elements in the sample plus non-good elements in the sample adds up to the total number of elements in the sample. And if you do all of the cancellation in here, you will get 0.2135. And I can just hear you across the continents telling me I don't want to do that cancellation. It's not that bad actually, but I agree. I wouldn't want to do that cancellation either. So what do you do next? You really hope your online textbook has a probability calculator for this. And luckily for you, it does. So let's go use it. Here's the same probability calculator that we used when we were doing binomial probabilities, and it is by default set to binomial. But we're not in the binomial setup anymore. We are doing the hypergeometric. There it is. And look, suddenly all the parameters change. So we have capital N is 52, yeah, the number of cards in the deck. G is not 26. It is 4, because it's the number of aces. N, the sample size, is indeed 13. It's a bridge hand. So 52 cards in the deck, aces are good. That's what I'm counting, the 4 aces in the deck. I'm sampling 13, and what do I want the chance of? I want the chance of getting 2 aces exactly. X is the random variable. It is the number of aces, the number of good elements. And you'll recall from the previous segment, you have here an option to do x greater than or equal to and or x less than or equal to. If you want equal to, then you want x to be greater than or equal to 2 and less than or equal to 2. And lo and behold, 0.2135, which is what we had by me doing the cancellation. So that's rather a nice way to get at hypergeometric probabilities without really having to break a sweat, once you have identified all of the parameters and your range of values that you're looking for. And the nice thing about this is that had I asked what is the chance that x is greater than or equal to 2, then there's my answer. Longhand, what would I have had to do? Longhand, either I would have had to add up the chances of getting 2, 3, or 4 aces, or I would have had to do 1 minus the chance of getting 0 or 1 ace. Either way, I would not have been happy. So it's really nice to have this swift little machine that does the calculation. So let's return now to one numerical example and one not so numerical. So we take another bridge hand, 13 cards out of 52, and now I want the chance of getting more than 7 red cards. And so my population is still the 52 cards. Successes are now red cards. And so successes correspond to 26 cards in the deck. I'm still dealing 13 and I want more than 7 red cards. So I'm looking at the hypergeometric setup. So a population size of 52, in the population 26 good elements, a simple random sample size of 13, and now more than 7 red cards. So more than 7, 8, 9, etc. up to 13. Why did I stop at 13? Because that's how many cards I'm choosing. I can't have 14 red cards in 13 cards. So how do I do this? Well, I have 2 methods. Either I add up all of these terms, so find this one using the hypergeometric formula, this one using the formula, this one, and so on, and then add them up, which seems to be a little bit of a tiring move. Or I can go to my trusty probability calculator in the text and just plug in n is 52, g is 26, little n is 13, and then your variable is greater than or equal to 8 and less than or equal to 13, and you will see 26.15%. Not so difficult. And so I would like to end with one situation in which you can't use your probability calculator because the problem doesn't have numbers in it. And this is the question of how likely is somebody to get into a simple random sample. And I'm going to pose it this way. I am in a population of size capital N. Somebody is going to draw a simple random sample of size little n, and I want the chance that I get into this sample. And what I'm going to do is I'm going to do this as a formal application of the hypergeometric, and then we will look to see if we can do it in some other way. Alright, so what's going on here? I've got a simple random sample. Am I counting good elements? You bet I am. I am the good element. And I want me in the sample. And so my setup is hypergeometric. That's the population size that's given. Capital G is 1. The set of good elements is me. The sample size, simple random sample size is given. How many good elements do I want? I want the 1. I want me in the sample. And so if I just plug in to my formula, it's good elements in population, choose good elements that I want in the sample, times not good elements in the population, choose not good elements in the sample, divided by population size, choose sample size. And there are a lot of things that look like they might cancel, and so we're going to be brave and just do this thing. 1 choose 1 is just 1. How many ways can you choose one item out of 1? There's one way, just choose it. Fine, so that's gone. This numerator here is by definition n minus 1 factorial divided by successes factorial, so little n minus 1 factorial, times failures factorial, so total minus successes. And when you take away the successes from the total, you get capital N minus little n. And so all of this portion is writing this top term in factorial notation. And the bottom, written upside down because it's in the denominator, is number of trials factorial, successes factorial, failures factorial. And so if you look at that, that's a lot of factorials floating around, but really that's a lot of smoke. Look, this cancels. Capital N minus little n factorial cancels, it's gone. What's this guy? That's little n factorial. This is little n minus 1 factorial. So this could be, for example, 13 factorial, and that's 12 factorial. That almost cancels. All you're left with is 13. And so there's your n there. And equally, capital N minus 1 factorial and capital N factorial almost cancel. The only term that remains is this n. And so what you've seen by a piece of algebra is that if somebody is going to sample little n out of capital N people as a simple random sample, and you are one of those capital N people, then your chance of getting in is little n over capital N. Now that's a simple little answer. And every time you get a simple little answer, it's worth examining it to see if there was a simple little way of getting at it. So what's it saying, for example? It is saying that the chance that I get in is the proportion that's being sampled. In other words, if somebody is taking a 10% sample as a simple random sample, then my chance of getting in is 10%. Well, it seems like we ought to be able to get at that directly. So we have a formula and we can do algebra, but we must not forget our basic methods. Right, so how do you create a simple random sample? You are drawing at random without replacement. That's the same as shuffling all the capital N names and taking the first little n. You've seen that with cards, just shuffle them all up. And then we take 1, 2, 3, 4 up to capital N. So where is my name on this list? Well, my name is anywhere in these capital N places. I don't know whether it's in the beginning, but it is definitely somewhere in all of the capital N names. And it is equally likely to be in any of those n places. My name is not more likely to be in any one place compared to any other. So then what is the chance that it's in the first little n places? Well, all of the places are equally likely, and so the chance that it's in the first n places is little n over capital N. In other words, if I had, say, 100 names on my list and I was sampling 10, then my name is equally likely to be in one of 100 places, and the chance that it's in the first 10 is 10 out of 100. That's a useful thing to keep in mind. First, that the chance that any individual gets into a simple random sample is the proportion being sampled. And the other is that every individual has this same chance of getting in. As an exercise, you might try to do this. Suppose my friend and I were both members of this population. You might want to try and figure out the chance that we both get in. How will it differ from what we've done here? Same population size, same sample size, good elements now. Yeah, both of us, my friend and me. So capital G will be 2. How many good elements do we want in the sample? We both want to get in. So little g is 2 as well. So you'll have 2 choose 2 here, capital N minus 2 over little n minus 2, and you do the calculation. And you see whether it's something that you recognize. In the next segment, I am going to do a sequence of examples